All right, so welcome back. We're starting our talks now. It's my pleasure to introduce Giorgia. She's an assistant professor at the University of Zurich and affiliated professor with ETH AI Center at the Chandler's University of Technology. Her research focuses on machine learning and mathematical modeling, with a focus on reinforcement learning and multi-agent learning. She has made foundational contributions to inverse reinforcement learning and multi-agent reinforcement learning, and she's going to be presenting about multi-agent learning from demonstrations. Take it away, Georgia.
Okay, thank you. I will put on. Super. Okay. So first of all, thank you for coming here, and thank you for inviting me to this workshop. I think it's a very nice initiative. So today, what I will talk about is two line of works that I worked during also like my PhD and postdoc that now I'm trying like to some way like bring together. That is like learning from without like reward functions, so from demonstrations and different kind of feedbacks, and also multi-agent learning. So why I'm interested like in this topic? The reason why is that multi-agent systems model like many different kind of real-world applications, going like from autonomous driving to energy systems, financial markets, and other kind like of money like healthcare. So basically, like our world is a multi-agent world, but we are continuing to look at like a single agent one. And one of the problem the multi-agent systems is that like the different agents that are like involved create like some sort of like complicated interactions that if you're modeling like in the wrong way, this will lead us to very like bad performances and behaviors. And defining the reward function as in like in single agent RL is very complicated. And in the case that we are like defining this reward function in a wrong way, this will induce miscoordination, conflict, and other kind of very bad behavior as I said before. So what is the solution to this? The solution is to use what we already know. So use like human knowledge to design like more safe human-aligned like multi-agent systems. And this is what like my lab is working on at the moment. And so what are like this is like something that is also like a very big topic in single agent. So I think that most of you like knows about like machine learning and behavioral cloning, universal preference-based in single agents, but maybe you don't know a lot like about on multi-agent systems because there is not a lot around. And what are like the main challenges that we will encounter or like we will find when we are going from single agent systems to multi-agent ones? One is that immediately we are observing like a group of agents who have like a specific behavior. One thing like that we have the problem is how to assign like the credits of like the different actions. What is like the reward function, the credit assignment problem like on a specific agent, and to understand what is like the credit of the other agents to his special like behavior. Another thing is that in single agents, the optimality criteria is quite clear. So what we are doing is that like the agent is maximizing like his expected return. Instead, in multi-agent systems is less clear. So there could be like different kind of optimality like criteria that makes sense, and this depends a lot on the application. Another problem is the sample complexity will like become like more bigger and bigger because like we have multiple agents involved. And this is something that we will see later, is that if you're making like a very small like error in one agent policy, this can create like a very big deviation on the other agent's behavior. So these are like the challenges that I'm describing to you like very like informally, and also like to start like the motivating part of this talk. But the first question that we need to ask to ourselves is if multi-agent machine learning is a real problem, or if you can use that like single agent approaches in order to solve like multi-agent also problems. So I will go like a step back and introducing you what is like the imitation learning problem in single agent. So in single agent, what we have is the following. We have an expert policy that is, I will call it 5-star, I hope during all the talk. Also, like the questions are the end, right? Okay. Because since we are like few people, it would be nice also to be interactive, but okay. So in imitation learning, like we can define two different settings. One is called non-interacting in the single agent imitation learning, and what's happening like in the single agent in the non-interactive setting is that we observe like these policies, that is an optimal policy, that is interacting with, like, with an environment. We are like is collecting data, and we are observing directly like this data set of trajectories. Then from this data set of trajectories, what we can do is that we can define like what is the optimal policy. And we want to define what is like the policy that the agent like is using without having access to the reward function. On the other hand, like in the interactive setting, is that what we're doing is that like our RL agent is directly like interacting with the environment. And what he can do is that he can ask for like information to the expert in order to have like information what is the correct in some way action to take in a different states. Like to give you like some names, like in the non-interactive setting, you can think about behavioral cloning. So it's sort of like a supervised learning problem. Interactive settings that you can think about other. What is the objective that we want to optimize in imitation learning, in single agent imitation learning is the following. So what we want to do is that we want to minimize the difference between the policy that we are learning and the policy that we are observing, so they're like the optimal one. But the problem is that like we want to minimize this objective, but we don't have access to the reward function. So what we can do is that we can use like some like proxy objectives, like for example, like in the behavioral cloning thing, that what we're doing is that we are solving like this supervised learning problem. We are trying like, to match what is the policy that we are observing. And there are different kinds like of policy losses that will be like were introduced. Like one could be like, for example, minimizing the L2 norm or minimizing like the log loss function. And this is like one way to see like the single agent imitation problem. Another way is what I call it adversarial approaches. There are all the approaches that are like, for example, in the lane of IQ-learn, Gale, and so on. And the idea behind like these adversarial approaches is that we want to find a policy that is minimizing the state action, the state action cooperation measure between the policy that we're observing and the one that we are like recovering. Okay, so this is the single agent imitation learning problem that I think that most of you knows. And the interesting thing is that like last year, up here, like this paper that showed that non-interactive BC have like very good performances, as like same performances in terms of the horizon at least, with like interacting behavioral cloning. In the case that we have access to deterministic experts, but we know that there is always a deterministic expert like in single agent. So, so cool, interesting. So when I read like this paper, like this came up like after one of the papers that we'll talk about multi-agent learning, I thought, okay, maybe we missed something because this is like seems so like too easy, like in some way, and maybe like also multi-agent will be the same, but we will see later that is not the case. So going from single agent to multi-agent, what we have is that a multi-agent, what we're observing is like many experts, so all the agents that are optimizing like a policy. We're optimizing like can mean like many different things. As I said before, they can optimize like, for example, the social optimum, the correlated equilibrium, the Nash equilibrium. And for this talk that are like what we assume is that the agent we are optimizing the Nash equilibrium solution. So this is like the first, I think, very interesting challenge that we have like in general, like in multi-agent is the fact that we can like define different kind like of objectives that the agent that we are observing are maximizing. But we need to start from somewhere, so we started from the Nash equilibrium. Okay, so our agents are maximizing the Nash equilibria with like the Nash equilibria like I mean that each agent will not like change his policy, will not deviate from his policy where we are fixing the policy of the other agents. So if we're fixing out the policy of the other agents, we have sort of like a single agent RL problem, and the agent is already like maximizing the single agent RL problem. Now we need to change also like our objective. So our objective is not anymore like the value limitation gap that we've seen before, but our objective will become like this that we call the Nash limitation gap, where like the Nash limitation gap, basically what you want to do is that you want to find a policy that is also like a Nash policy. As before, we don't have access to the reward function. So like the first question we need to pose to ourselves is if we can use directly like single agent proxies. So like behavioral cloning and adversarial approaches also for multi-agent problems, or if we need something different. And a second question like that we will see like in this talk is if no-interactive, like the set interactive intentional learning setting is enough also in the multi-agent case. Okay, so I will start like by this work that we presented in RLC 2023 that was like on mean-field games. So I don't know how many of you knows about mean-field games. Raise your hands. No? Okay, super. So I will give you like a short introduction on the very cool world of mean-field games. So the idea behind mean-field games is the following, is that we have now like an infinite amount of agents. And this, since like the agents are so many, we can see it like each agent as like part of the system. And we consider that each agent are using like the same policy. So like this agent that we are like picking basically is called a representative agent. And this representative agent like is following a policy pi as all the other agents in the system. And the policy pi induces like a state action distribution that will change basically our like transition model. Because the transition model and the reward function will depend on the state action distribution that is induced by the policy. So you can see that we are changing the policy, changing the state action distribution, so changing also like a transition model. And so this policy could be not optimal anymore, so you need to change the policy again, and so on. And this creates like a very could be like also complicated game in some cases. And the solution concept that we have here is called mean-field like equilibrium solution. And the idea is like the same as the one before, is that when we're fixing basically the state action distribution of like a policy, of the policy pi star that we are like trying to understand if it's Nash equilibrium policy, if this policy is optimal with respect to this, like the state action distribution that induce, then it's a Nash equilibrium, because you don't want to deviate from what like also the other agents are playing. Okay, so I hope that was like clear, like what is like a mean-field game, at least to have like the sense like of what is. So what is like the mean-field games like imitation learning problem is the following. So imagine that we are like observing like a population that is playing like a Nash equilibrium problem. Then like we have like our agent that is observing like the problem. And if you think about like from a single agent point of view, what we can do is that we think about this agent like he's copying, like he's imitating the policy, and then like he's using like this policy like only with the population, but the population remains fixed. Clearly, like this violates in some way like the spirit of the mean-field game, because in a mean-field game, as we say, like each agent are playing the same policy, and like the policy that we are now using will also change the distribution of the other agents. So what we need to do is that we need to go from like the single agent point of view to like the multi-agent one, when like the agents are observing, they're changing their policy, and like this policy will induce also like a new state action distribution. Okay, so I hope that you can see like the differences like in perspective of these two kind of problems. What is like the first step that we did is that we like look at the two proxies that I introduced before, so the behavioral cloning one and the adversarial learning one, and we like estimating like our Nash limitation gap that I hope that I call also before an IG, but will be like this is the acronym that I will use during the presentation. And as you can see, like what we have here, we have like this very bad dependency on the horizon. So in the sense that if we have like an epsilon error on our in our behavioral cloning step, we will have like this exponential dependency on the horizon. And if we have like if we use like more sophisticated like approaches, like adversarial learning approaches, also in this case we have like this exponential dependency that could be very bad. So the reason why that we have like this, like for intuition, the reason why we have like this dependency is because we have like that also the transition model depends on the error that we are making, like producing like the new state action distribution and like having like an exponential error. So what this means is that single agent methods are not enough. And so we then need to come up with different proxies for the multi-agent learning problem. So what we need to do is that we need to go from like trying to minimize it, like state action conventional measure when we are like fixing the distribution of like the Nash equilibrium policy, to a new one that's used directly like the distribution on the policy that we are learning. So here the meaning of this is that like you have like your policy, and this is like the distribution of the game. Instead here, like both like the policy distribution of the game are induced like from the same policy. So what we show is that like if you're going like from minimizing like this loss function to minimizing what we call the mean field control adversarial learning problem, what you can have is that now you have like again like a very like a good dependency, like a square dependency on the horizon, and we are like removing like the problem on the exponential dependency on the horizon. So we have also provided like some sort like, okay, this is like quite interesting, like this illustration, because what we had before, someone can say that is like only an upper bound. That is true, it's only an upper bound. So maybe like this upper bound, exponential upper bound can be very loose. And then like instead, like we have like some problems like in our proof. But like instead we came up like we have sort like of experimental lower bound, where we're showing that like for this kind of game, we have like an exponential like problem when we have like increasing like the horizon, as you can see, for the behavioral cloning and for the adversarial learning proxies, while instead like for our new proxy, we have like a good dependency. Okay, so like with this first work, what we answered is the fact that we need new kind of algorithms in order to solve like multi-agent induced learning problems, and we cannot use like single agent mutation ones directly. And in the second part of the talk, I will show you like instead like how to answer to the second question, that is like if interactive, not interactive, like industrial learning is enough also in a multi-agent setting. So this is like a recent work that's my PhD student like did, and so the idea like this. Now I will go back to the normal Markov games that I think that most of you knows about. And for easy like explanation during like the talk, I will only talk about two-player sum games, but our results can be also generalized to general sum like n games. So one thing that is different from the work before is that now we'll talk about like discounted setting. So like infinite horizon discounted setting and not anymore like finite horizon setting. And what we have now is like a two-player zero-sum game. So we have like our two agents, mu and nu, that are playing like their actions, and we have like the reward function, and for one like is positive, for the other one like is like the negative part, like the negative negation of this like reward function. So this is like the question that we were like trying to answer, and to do it, what we need to do now is to do like different steps. The first step that we did is the following. So what we have now is like that our Nash imitation gap can be divided like in two different parts. The first one depends on the error that we have like on the policy new at, and the second one is the error that we have on the policy new at. So one is the policy of like of the optimizer, and the one like the policy of the minimizer of the game. So if you look at these errors, so these errors, what have like inside, they have like the best response. So we have like our, okay. I use now like this, I'm very sorry. I hope that's like I use always like the same notation, but it's not like this. So new at new A is the same thing. So I'm referring to like the best response on the policy that we are recovering. That is like this new at is the same thing. And here like we'll do like also like the same. I think that for the rest of the talk I always use new A. But okay, so what we have here is that we have like the difference between the best response on the policy or like on the policy that we are like using, and then like the best response on like the policy that we have used and the policy that we're serving. And this error can be bound by like the total variation of like the optimal policy that we're serving, so the expert policy, the equilibrium one, the one that we are recovering, due to the expectation on the policy that is the best response to the policy that we are observing. So I feel that after that, like we'll have like an example, this will be like more clear. But like trust me, that it's like this. So what we showed is that the first thing we show is that like the Nash imitation gap is upper bounded by this quantity. That's this quantity, what is the deviation of the best response of the recovered policy and the equilibrium one. So what this means is that how much change like our state action distribution with respect to the best response the recovered one with respect to the Nash equilibrium one that you're observing. And we call it like this concentrability coefficient for the rest of the talk. So as before, this is all like an upper bound. So we come up also like with a sort of like of lower bound. And our lower bound is quite interesting, I think. And there were also like similar like results, but like in another paper that was already like presented last year in Zurich. But what we show like in these lower bounds is that this Nash like imitation gap can be like constant and cannot be reduced. Like also like if you're using like every kind of algorithm that we want, that's like trying to minimize the not interactive machine learning problem. And this is because there exists a game where this concentrability coefficient is infinite. And so we cannot like reduce this concentrability coefficient. And this like the interesting part is that it's also if we know exactly what is a transition model. And this is quite different from what we have like in single agent, when in general like the real problem is like estimating a transition model. So this is like the idea like behind the lower bound. So what we have is that we have like imagine that this is the policy that we are observing. So it's this blue one, and we are recovering like perfectly like this policy. So we have like we know perfectly what is this, but the problem is that like we have very like small probability. Also like not with small probability, like we can be also like deterministic, but we have like that there is this policy, but then like what we have is that we are making an error like on this state. If we're making like an error on this state, like our agent, what can do is that he can like the other agent can exploit this error in order like when we are going like to this state, like with this very small probability that I was saying before, we are not going anymore to the correct like paths, but we're going to something that can like be like very bad for us. So they can like exploit like in some way our weakness. And we cannot do anything like we have like an infinite amount of samples. And the reason why we cannot do it is because we're observing like only like the trajectory of our expert. And this is important because Also, like if it's deterministic, like this thing, as you can see, like this transition depends also on the policy of the other agent, not only on our policy. So if the other agent is not playing this B3 anymore, he will start playing this, and we are going like this part of the environment, and we don't know what to do. So what is the meaning here is that if you're doing also like perfectly our behavior cloning with an infinite amount of samples, we can have like very bad STEM behaviors like in a multi-agent setting. So what we need to do is that we need to have like an interactive algorithm for imitation learning like in multi-agent systems. And we propose like two different algorithms. I will talk a little bit about the first one now. So in the first one that they call it like this one way. What we did is that we assumed to have access to the best response oracle. So we have access not only to the Nash expert, but also like to an expert that every time that we are changing the policy will best respond to our policy. And if you remember, like before, what we have is that like in order like to minimize like the Nash imitation gap, what we need to do is that we need to minimize the total variation between the policy of the expert policy and the recovered policy. The problem is that this minimization problem is non-convex, and we need also to collect the data from like the expert policy and the best response every time, and we don't have like this possibility. So what we have showed instead is that like instead of minimizing this is enough to minimizing like the differences between like the expert policy and the policy that we are like at the moment like minimizing. Because then like our player, like our agent will also like play this best response. So expectation will be like covered. And this depends only on UK, not anymore on this max. And to solve like this, to minimize like this expectation, what we can do is that we can use like some no-regret algorithm for like to these loss sequences and continue to apply them. And what we showed is that like the sample complexity in this case, that like this algorithm does not depend anymore on this concentrability coefficient that we have before. So we avoid like dependency on these like terms that can be also like infinite. We have like a worse like dependency on the epsilon. So we have like this epsilon over 4 instead of epsilon over 2. And it will be like interesting to understand if it can be reduced. And then like the question now that we can have is how to remove the best response oracle assumption. And we will see it like in a few minutes because like it's one of the papers that we're presenting here and it's like on one of the spotlight. So I will conclude, I think on time, I hope, is 28 minutes on my laptop that I'm talking. So with like some takeaway messages. No, it's not the best slides, I think, of the presentation, but so I hope that like my message of like this talk is that multi-agent learning problems can have like very new challenges and interesting challenges like to be solved in the imitation learning like setting. And we need to carefully like design like new algorithms to solve these challenges. And these new algorithms also needs new trick and interesting like thought from like behind them. So I think it's like a very interesting topic that I hope that now you're also interested into. And we need to make, like I said before, we need to make also the correct assumption with respect to the setting that we are considering, because like we assume now that we are observing Nash equilibrium policy, but like in many other cases, we are not observing Nash equilibrium policy, but we can observe like a different kind of like of expert in the multi-agent scenarios. So thank you, and I don't know if we have time for questions.
One or two questions?
Super.
Quite interested. So yeah, we should. Are there any questions from the audience? Yes.
Yeah.
Yes. First one, like multiple Nash equilibria in games. So you have thoughts on like maybe some Nash equilibria like easier to learn than others. So it might be also like a useful question. And the others like we can also like want maybe transfer between like these sort of like things that you learn. Because imagine if you have an environment when you observe one Nash equilibria once, but then when you go in the real world, you have a different Nash equilibria. And if there's like information you can transfer to one.
So my first question is some today I told before, even though we don't about university wasn't very motivated systems, and we are on two discussions. So one thing that you need to figure that is communication. Like it's we can't like this this all around only because it could be like concern about the resolution. So in case there is only a partnership with the solution, we don't have this problem because yeah, we don't like this one that being on the dictionary. So if I have only the partnership with you, we can solve it. So one thing to be like the arts and categorization to the game and so the categorized problem. The other like I have this so that is how to like how to design different like queries different like aspects in order that you select different like shipping policies. And I feel like working scale like this also like opting to do this difference between the English learning and IFL. In the case of English learning, we are communicating without like really understanding how to validate what's needed to maximum inside the way of the
Thank you. Let's thank our speaker again, and then we'll move. Very interesting. All right, and then our next up will be spotlight talks. So,
Oh.
yeah. Use them out.